If you were to build the most powerful telescope allowed by the laws of physics,
Right.
like a lens so perfect, so impossibly massive that it could see 500 billion light years into the void,
Yeah.
you wouldn't see distant, ancient alien civilizations. You wouldn't see, the birth of exotic, unheard of galaxies.
No, you wouldn't.
You would see absolutely nothing because you'd be asking for light that just, well, it doesn't exist yet. You'd be hitting a wall built not of distance, but of time.
Exactly.
Welcome to a journey into the ultimate limits of reality. I mean, we are pulling apart a massive stack of cosmological models and philosophical frameworks today for this deep dive.
It's a lot to cover.
It really is. Our goal today is to explore the age and the sheer mind-bending scale of the cosmos.
And we are stepping far outside the bounds of human intuition here. We're moving past the comforting local physics of our everyday lives.
Right, the stuff we can actually touch.
Yeah, and we're moving into the mechanics of deep time and expanding space.
Which is just, it's wild.
Yeah.
We want to understand why the scientific consensus has locked in on the universe being exactly 13.8 billion years old. And, why do the models insist the observable universe is 93 billion light years across? Which, if you think about it, seems to mathematically contradict that age.
It definitely sounds like a contradiction at first glance.
Right. And then finally, we're going to explore whether everything we've ever observed might just be a single localized water droplet in a vastly larger, eternally inflating multiverse.
Which is a heavy concept.
Totally. Now, you've probably heard that 13.8 billion year figure and just, accepted it. But if you're anything like me, a part of you is always whispering, wait, who actually measured that? And how?
And that skepticism, that is the driving force of cosmology.
Is it?
Oh, absolutely. When dealing with scales this immense, throwing out a very specific number like 13.8 billion feels incredibly audacious.
It's still like a total guess.
It sounds like an untestable assumption, yeah. But the critical distinction to make right away is that 13.8 billion years is not a starting assumption just to make the math work.
Right.
It is the inescapable conclusion. It's the destination we are forced into after testing the mechanics of the universe through completely independent methodologies.
Okay, let's unpack this. Before we try to wrap our heads around the outer limits of a 93 billion light-year sphere, we have to establish when the clock actually started ticking.
We need a starting line.
Exactly. And the models we are looking at today, they don't just rely on one clock. They detail 3 independent mechanisms.
Yes, 3 distinct physical regimes.
Right. So if we want to claim this massive number isn't just a blind guess, we need to look at how these 3 entirely different fields of physics end up, pointing to the exact same second.
Because convergence is the ultimate currency in empirical science.
Convergence, meaning they all agree.
Right. If you measure the same phenomenon using entirely different physical laws and you get the exact same answer,
the probability of it being a coincidence just drops.
Right. It drops to near zero. It's virtually impossible. And the first and arguably most profound of these clocks is the cosmic microwave background, or the CMB.
The residual radiation snapshot.
Exactly.
We talk about the CMB all the time on these deep dives, but the actual mechanics of using it as a literal clock are just fascinating.
It's incredible.
I mean, we are looking at the leftover heat from the Big Bang, but it's not like you're just reading a literal timestamp printed on the sky.
Far from it. To use the CMB as a clock, you really have to understand the physics of the early universe.
Okay. Take us there.
So for the first few 100,000 years, the universe was so hot and so unimaginably dense that it was essentially an opaque plasma.
Like you couldn't see through it.
Right. Photons, which are particles of light, they couldn't travel any meaningful distance before smashing into free electrons.
So the light was just bouncing around constantly.
Yes. The universe was glowing brightly, but it was foggy.
Wow. So no light could escape at all. It was just a trapped, superheated soup of particles.
Exactly. Then space expanded. And as it expanded, it naturally cooled.
Because the energy is spreading out over a larger volume.
Right. And at a very specific temperature threshold, things finally calmed down enough for those agitated electrons to bind to protons.
Forming actual atoms.
Yes, forming the very first neutral hydrogen atoms. We call this the epoch of recombination.
Recombination. Okay.
And suddenly, all those electrons were locked up. The fog just lifted.
Oh, wow.
The universe became transparent, and all those trapped photons were finally free to just travel in a straight line across space.
And the CMB is that exact moment, that first burst of liberated light.
That's the CMB. And by measuring the exact temperature of that radiation today, which, has cooled down to just a few degrees above absolute zero,
Right.
we can work backwards through the known thermodynamics of expanding gases. Cosmologists can calculate precisely how long that light has been cooling.
And that thermodynamic timeline gives us roughly 13.8 billion years.
Yes, exactly 13.8 billion years of cooling.
Okay, so that covers the ambient temperature of the room, so to speak. But the second clock from the source material looks at the actual furniture inside the room.
The stars themselves.
Right, the observation of the oldest stars and globular clusters. And this requires a totally different branch of astrophysics, doesn't it?
Completely different. We aren't measuring stretching light and cooling gases anymore. We are measuring nuclear fusion.
Okay, how does that work as a clock?
Well, stellar evolution is strictly governed by the laws of quantum mechanics and nuclear physics. We have highly detailed, tested models of how stars burn their fuel.
Because different stars burn at different rates.
Exactly. And when we look at globular clusters, which are these dense spherical collections of ancient stars orbiting the galactic core,
Yeah.
we are looking at populations of stars that all formed from the same cloud of gas at roughly the exact same time.
Oh, so it's like a graduating class of stars.
That's a great way to put it. And observing their life cycles acts as a very precise timer.
Right, because a massive blue star burns through its fuel incredibly fast, right? It dies in just a few million years.
Yes, they live fast and die young. But a small red dwarf, it can sip its hydrogen slowly for trillions of years.
Trillions. Wow. Okay, so how do we use that graduating class to tell time?
By analyzing the spectrum of light from a single globular cluster, astronomers can map out all the types of stars that are still burning.
And the ones that are already gone.
Right, the ones that have already exhausted their fuel and turned into white dwarfs. They look for what's called the main sequence turnoff point.
The turnoff point, meaning the exact mass of the stars that are just now dying today.
Precisely. The mass of the stars that are just now blinking out tells us exactly how long that cluster has been sitting there burning its fuel.
That is so clever.
It really is. And when we find the oldest, most metal-poor globular clusters in the universe, their chemical clocks tell us they have been burning for roughly 13.5 to 13.8 billion years.
Which just perfectly aligns with the cooling of the CMB. Because, I mean, you literally cannot have a 15 billion-year-old star sitting in a 13.8 billion-year-old universe.
It would break physics. The timeline of nuclear fusion matches the timeline of thermodynamic cooling.
Which brings us to the third clock, which is the big macroscopic one. Hubble's law and the expansion rate of galaxies.
The physical movement of the universe.
Right. Let's use the cars on a highway analogy from the sources here to visualize how cosmic expansion actually measures time. Because I think this one is really intuitive.
It is a highly effective way to conceptualize it.
Yeah, so imagine standing on an overpass, looking down at this vast, flat plain. And there's a highway network spreading out in all directions from a single central parking garage.
Right. And you observe all these cars driving away from that center.
Yeah. Some are close by, and they're moving pretty slowly. Some are, 50 miles away already, and they're moving much faster.
But if you measure their current distance and their current velocity, you don't just know where they are going.
You can calculate exactly how long they've been driving.
Yes. You just trace the vectors backward. You are basically hitting the rewind button on the expansion.
Okay, so how do we actually do that with galaxies?
In cosmology, we measure the distance to galaxies using standard candles, things like Cepheid variables or Type Dia supernovae, which have a known fixed brightness.
So we know exactly how far away they are.
Right. And then we measure their velocity, how fast they're moving away from us, by observing how much their light has stretched.
The redshift.
Exactly, the redshift into the lower frequencies of the spectrum.
So we have their distance and we have their speed.
And when you apply the equations of general relativity to wind that galactic expansion backward in time, all those massive structures converge.
Shall go back to the start.
Yes, back into a singular state of infinite density.
All the cars arrive back in the central parking garage at the exact same moment.
And that exact moment was 13.8 billion years ago.
Wow. So the thermodynamic cooling of the background radiation, the quantum mechanical burning of the oldest stars, and the relativistic rewinding of expanding galaxies?
Yes. 3 independent physical regimes.
In one single number.
What's fascinating here is the sheer philosophical weight of this convergence.
What do you mean?
Well, an amateur skeptic might argue that our measurements of redshift are somehow flawed. Or maybe they argue that the garage wasn't actually the true beginning.
Sure, people debate the Big Bang all the time.
But the fact that stellar chemistry and primordial thermodynamics independently agree with the macroscopic expansion, it locks the conclusion into place.
Because they have nothing to do with each other mechanically.
Exactly. It leaves virtually no conceptual room for the universe to be significantly older or younger.
Right, because if the universe were, say, 100 billion years old, the stars would be entirely dead by now.
The CMB would be completely undetectable, and the expansion vectors just wouldn't point to a cohesive origin.
Okay, having that anchored feels like a really solid foundation. We know the age.
We do.
But this is exactly where the models introduce a glaring, massive contradiction.
The spatial paradox.
Yes. Because once you accept the 13.8 billion year timeline, you immediately run into this paradox. If the universe has only been expanding for 13.8 billion years, how on earth is the observable universe 93 billion light years across?
It sounds impossible.
It really does. I mean, if we take a light year as a rigid unit of distance, this implies things have traveled vastly faster than the speed of light to get that far away from the center.
Right.
Which obviously breaks the fundamental rule of physics. Nothing moves faster than light.
And resolving that paradox requires us to completely abandon our intuitive understanding of space.
Okay, abandon it how?
Well, we naturally think of space as a static container, like an empty room or a theater stage.
Right, and the galaxies and photons are just actors moving across the floor.
Exactly. Under that Newtonian assumption of a static stage, yes, the universe could only have a maximum radius of 13.8 billion light years.
Because light only had 13.8 billion years to travel.
But the stage isn't static. General relativity demands that space itself is a dynamic, malleable substance.
So space isn't just emptiness.
No, space is a physical metric, and it is actively stretching.
Wow.
The observable universe is 93 billion light years across today because space was continually expanding while the light was making its journey toward our telescopes.
Okay, I find the ant on a rubber band analogy from the text really crucial for making this click.
It's the best way to visualize it.
Yeah, so imagine an ant representing a photon of light. The ant is walking across a long rubber band, which represents the fabric of space.
Right.
The ant walks at a constant maximum speed, which is the speed of light, and it's heading directly toward you.
But as the ant takes each step forward, an external force is actively stretching the rubber band.
A rubber band is getting longer.
The surface the ant is walking on is literally growing beneath its feet.
So the ant still perceives itself as walking at a constant speed.
Yeah.
But the total distance it has to cross just keeps compounding.
Yes. It takes billions of years to reach the end of the rubber band.
And here's the crucial realization. By the time that photon of light finally reaches your eye, the point on the rubber band where it started its journey has been pulled vastly farther away.
Exactly. When we look at a galaxy whose light has been traveling for 13 billion years, we are seeing the light as it was emitted in the distant past.
Right.
But the actual galaxy itself, carried by the expanding metric of space over those 13 billion years, has been pushed tens of billions of light years away from us in the present day.
Because the space between us and the galaxy expanded while the light was in transit.
Yes. We are looking across a stretching canvas, measuring what we call co-moving distance.
Co-moving distance. So we are essentially seeing an object that is currently 46 billion light years away from us, using light that only took 13 billion years to arrive.
That is the math.
Yeah, that concept is just dizzying. And it establishes the absolute boundary of our reality, doesn't it? The cosmic horizon.
The cosmic horizon is the absolute physical limit of observability.
Walled in by time.
Yes. Because the universe has a finite age, and because the speed of light is a hard limit, there is a maximum distance from which any information could have possibly reached us.
Right.
Light originating from beyond that 93 billion light-year sphere simply hasn't had enough time to cross the expanding space between us.
So we are completely walled in. Which brings me back to the hypothetical scenario I posed at the start of the deep dive.
The super telescope.
Yeah, because my human instinct, looking at that hard boundary, is to just try and engineer my way out of it.
It's a natural urge.
If there are galaxies sitting out there at the, say, 200 billion light-year mark, why can't we just build a better tool?
Right.
Put a massive telescope array in orbit around Jupiter, scale it up exponentially. Why can't a sufficiently advanced civilization see 500 billion light-years away?
Because that assumption treats a telescope purely as a spatial magnifier, like a giant zoom lens on a camera.
Which it is, right.
Spatially, yes.
Yeah.
But we have to reevaluate what an observatory actually does. A telescope does not reach out and touch distant objects.
Right, it just catches what comes to it.
Exactly. It passively catches light that has naturally fallen into its mirrors. A telescope is, at its core, a time machine.
You're capturing the past.
Always. When you look at the sun, you see it as it was 8 minutes ago.
And the Andromeda Galaxy we see as it was 2.5 million years ago.
Yes. Looking deeper into space inherently, unavoidably means looking further back in time.
Oh, okay. I see where this is going.
So when you propose a telescope that can see 500 billion light years away, you aren't asking for an engineering marvel.
No.
You are asking for the laws of causality to break. You are asking to see light that left its source 500 billion years ago.
But the universe is only 13.8 billion years old.
Exactly. The universe didn't exist 500 billion years ago.
So you are literally asking to observe a photon that does not exist.
Right. No amount of mirror polishing or digital enhancement can detect light that was never emitted in the first place.
Wow.
The barrier isn't the physical limit of our technology. It is the fundamental limit of time itself.
So what does this all mean? It means our blindness to the rest of the universe isn't a failure of engineering. We are boxed in by chronology.
Yes.
We can't look further out because eventually our gaze hits the moment before light even existed. We just hit the wall of the Big Bang.
And it forces a profound humility upon observational science. We are permanently trapped in a sphere of causality.
But the math doesn't just stop there, does it?
No. Theoretical physics provides tools to extrapolate what lies beyond that wall. We know the universe didn't just abruptly stop at our horizon.
Right, there has to be more.
To explain the vastness and the very specific properties of the space we actually can see, the models rely heavily on the theory of cosmic inflation.
And the inflaton field. Let's get into the mechanics of this inflaton field, because I think it's vital to distinguish this from the standard expansion of space we were just talking about with the rubber band.
It is a vital distinction.
Because the standard expansion, dark energy pushing galaxies apart, is relatively slow and steady, right? Over billions of years.
Yes. But inflation is a completely different, violent beast.
Violent how?
Standard metric expansion has been happening for almost 14 billion years. Inflation was an event that occurred in a fraction of a microscopic second immediately following the Big Bang.
A fraction of a second.
Yes. Theoretical physicists postulate a scalar field, the inflaton field permeating all of space.
A scalar field. We should clarify that because it sounds really intimidating.
It does.
It's essentially just a field where every single point in space has a specific value or energy level attached to it, right? Like a massive topographical map or a room's temperature distribution.
That is a perfect visualization. Unlike a magnetic field, which has a direction and a physical pole, a scalar field just has an energy state at every point.
Okay, so what did this specific field do?
The model suggests that in the earliest possible moments, this inflaton field was in what we call a false vacuum state.
False vacuum, meaning it wasn't stable.
Right. It held an enormous amount of potential energy. It was perched like a massive boulder at the very top of a steep hill.
Just waiting to fall.
And when that field inevitably rolled down the hill to its true minimum energy state, it released all that pent-up energy.
And that energy went where?
It drove space itself to stretch, to expand at an incomprehensible exponential rate.
And this was needed to solve the horizon problem, right?
Exactly.
Because without inflation, we couldn't explain why opposite sides of the observable universe regions that are 90 billion light years apart today and have never been in contact had the exact same background temperature in the CMB.
Right. If they've never touched, how do they share their heat to become the same temperature? Inflation solves that.
How?
It proposes that the entire observable universe was once a single, subatomic, intimately connected patch of space.
So it was small enough to equalize its temperature.
Exactly. It had plenty of time to reach equilibrium. And then inflation violently stretched that microscopic patch to macroscopic scales.
Faster than the speed of light.
Much faster. It ironed out all the cosmic wrinkles, resulting in the flat, uniform universe we observe today.
But the sheer scale of that stretching is where human comprehension just snaps for me.
The numbers are absurd.
Yeah, the mathematical models state that to solve the horizon problem, the universe had to expand by a minimum factor of 10 to the 26th power. That's a 1 with 26 zeros.
And that is merely the lower bound. That's just the bare minimum required to make the math work for our specific observable patch.
Right.
But the physics of scalar fields strongly suggest that inflation wouldn't just elegantly stop the moment it satisfied our local equations.
Why would it? It doesn't care about us.
Exactly. Natural models of inflation allow for exponential growth factors of 10 to the 100th power, or even 10 to the 1000th power.
Which just, I can't even picture that.
Nobody can. If inflation lasted even a billionth of a second longer than the minimum requirement, the universe is functionally infinite.
Meaning our entire 93 billion light-year sphere, which contains trillions of galaxies, is just an imperceptibly tiny rounding error in the true volume of reality.
Yes. It completely reframes the Copernican principle. Well, not only are we not the center of the solar system or the center of the galaxy.
Our entire observable universe is just an arbitrarily small, random patch of a structure we can never possibly map.
Exactly. We are a speck inside a speck.
Which naturally leads us to the most dangerous question in cosmology.
Uh-oh.
What if our fundamental assumption about that larger structure is wrong? Everything we've discussed today, the precise 13.8 billion year age, the uniform expansion, the elegant math of inflation, it all rests on one thing: the cosmological principle.
The bedrock of modern cosmology.
Right. The assumption that the universe is homogeneous and isotropic. Meaning, if you zoom out far enough, every part of the universe looks exactly the same, with matter evenly distributed everywhere.
Yes. The cosmological principle is the load-bearing pillar of the Standard Model.
Because without it, the math breaks.
Completely. If you drop the assumption of homogeneity, the complex equations of general relativity become almost impossible to solve for the universe as a whole.
So we just assume our local neighborhood is a fair representative sample of the entire cosmos.
We have to. It's the only way the models function.
But looking at the deepest maps of the CMB from the sources, there are structural cracks forming in that pillar.
There are anomalies, yes.
This is what some cosmologists call the CMB heresy. The blueprint of the early universe is actually not perfectly uniform. There are glaring anomalies.
We are talking about specific, large-scale features in the cosmic microwave background that simply shouldn't exist if the universe expanded uniformly from a perfectly random quantum state.
Like what? What are we seeing?
The most famous anomaly is the cold spot. It's a massive region in the southern celestial hemisphere that is significantly cooler than the surrounding radiation.
And that's a problem.
A big one. The probability of such a large fluctuation occurring by random chance in the Standard Model is remarkably low.
And it's not just a single spot either, right? There are structural alignments.
Yes.
Like the axis of evil, which honestly sounds like a political thriller, but it's actually a bizarre alignment in the cosmos.
It's an alignment of the universe's quadrupole and octupole moments.
Right, which are essentially the largest vibrational harmonic waves of the CMB.
Exactly. And they all inexplicably line up along a single axis pointing in a specific direction.
Which shouldn't happen in a random universe. And we also have hemispheric asymmetry, where one half of the sky just has stronger temperature fluctuations than the other half.
The universe appears somewhat lopsided.
Lopsided.
And this raises an important question that actively divides the cosmological community today.
Which is?
Are these anomalies merely statistical flukes, or are they empirical evidence that the cosmological principle is fundamentally flawed?
That's a huge debate. Where does the data stand right now?
Currently, the statistical significance of these anomalies hovers around the 3 sigma level.
Okay, let's clarify that for the listeners.
Right.
In physics terms, a 3 sigma result means there's roughly a 99.7% chance the signal is real data, right? Not just instrument noise.
Right, it's a very strong signal.
It's enough to make a theorist sweat, for sure. But standard particle physics usually demands a 5 sigma certainty, which is a 99.9999% chance before declaring a definitive discovery and rewriting the textbooks.
Exactly. So we are in a state of high tension.
Waiting for better data.
Yes. But if the 3 sigma anomalies hold true with future higher resolution observations, the implications are devastating for the Standard Model.
Devastating how?
Well, if the universe is genuinely patchy on the grandest scales, exhibiting sheer structural asymmetry, then the uniformity we thought we saw was just an illusion created by the limited scope of our cosmic horizon.
Oh, man. If the universe is patchy, then our calculations of 13.8 billion years might only apply to our specific patch.
That is the consequence, yes.
We might just be sitting inside a localized Hubble bubble.
Yeah.
Like a massive underdense region of space where expansion just behaves differently than the universal average.
And if that's true, Our measurement of deep time becomes purely local.
Just local time.
Wow. That heterodox perspective fundamentally changes the nature of reality. If our 13.8 billion years is merely the local time of our specific patch, it forces us to confront what lies outside the patch.
And how these different regions might interact.
Yes.
Here's where it gets really interesting. This brings us to the grandest framework presented in the models.
The multiverse.
Exactly. Combining the mechanics of scalar fields with the breakdown of the cosmological principle, eternal inflation.
It is a stunning theory.
And the analogy used to visualize this in the text is profoundly elegant. Imagine we are a microscopic organism, a microbe, living entirely within a single water droplet.
A completely localized, contained environment.
Exactly. This droplet is resting on the surface of an impossibly massive, ever-expanding green leaf.
Right.
As the microbe, we look around and map our entire reality. We measure the circumference of the water, we calculate how long it took the water to form, and we definitively declare this is the entire universe, and it is 13.8 billion years old.
Because that's all the microbe can see.
Right. We are completely, entirely blind to the existence of the leaf.
And in the theory of eternal inflation, the leaf represents the eternally inflating background space.
Oh, so inflation didn't stop.
No. The inflaton field we discussed earlier, it didn't just expand once and turn off everywhere simultaneously.
A single big bang.
Right. The mathematical model suggests that the violent, faster-than-light expansion of the scalar field is actually the natural, permanent state of reality.
It is inflating endlessly.
Endlessly.
So wait, where did the droplets come from then?
The droplets are bubble universes. They are created through a quantum mechanical process called false vacuum decay, or bubble nucleation.
Bubble nucleation. Okay, paint that picture for us.
Imagine a pot of boiling water. The rapidly expanding steam represents the eternally inflating space.
Fast, violent expansion.
Right. But the liquid water drops forming within the steam, those are regions where the inflaton field randomly decayed into a lower energy state.
Oh, so in that specific localized region, the violent exponential expansion suddenly stops. The boulder rolls down the hill, releasing its energy.
Precisely. That release of energy cascades into the creation of matter and radiation.
A big bang.
Yes. So our Big Bang, 13.8 billion years ago, was not the beginning of everything.
It was merely the moment our specific local bubble nucleated and stopped inflating.
We are living inside one droplet.
That is just wow. And out there on the leaf, across the eternally inflating background, countless other bubbles are popping into existence constantly.
Yes. A true multiverse.
Not like parallel dimensions layered on top of us like you see in sci-fi movies, but actual physical regions of space separated by vast expanding gaps.
Real physical distance, yes.
Yeah.
And each bubble could have its own laws of physics. Different particle masses, different dimensions, and completely different ages.
Different ages. So there could be bubble universes that nucleated trillions of years before ours.
Easily. Trillions of years older.
Which circles me right back around to my obsession with looking past the horizon.
The telescope again?
Yes. Because if there are older bubbles out there on the leaf, why couldn't our microbe ever build an instrument sensitive enough to see the light radiating from an adjacent droplet?
It's a fair question.
I mean, if they exist in the same overarching physical framework, the same leaf, shouldn't their light eventually cross the gap and reach us?
It is a logical hope. But the physics of the leaf creates an insurmountable barrier.
Why?
Because the space between the bubbles, that eternally inflating background, is still expanding violently.
Right, it never stopped.
And it is stretching apart infinitely faster than the speed of light.
Oh, so the gap between the droplets is widening faster than a photon can travel.
Exactly. It functions as an absolute one-way door in space-time.
So even if a neighboring bubble universe is unimaginably old,
and even if it emits a blinding torrent of light in our exact direction,
we still wouldn't see it.
No, because that light is trying to cross an intervening space that is physically multiplying. The light is dragged backward relative to the expansion.
Like trying to run up a down escalator that's speeding up?
Yes. It can never, ever cross the threshold into our bubble.
So we are fundamentally permanently isolated by the mechanics of metric expansion. The microbe can never perceive the other droplets.
Never. And if we connect this to the bigger picture, to the broader philosophy of science, it fundamentally alters our relationship with empirical truth.
How so?
The realization that we cannot see these other bubbles, it isn't a failure of human ingenuity.
It's not a lack of funding for better telescopes.
Right. It isn't because our mathematical models are weak or our tools are bad. It is a hard physical limit imposed by the relativistic laws of expanding space.
Wow. Just wow. Let's trace the arc of what we've mapped out today for the listener, because we've covered massive ground.
We really have.
We started with the rigorous empirical triumph of the 13.8 billion year consensus.
The 3 clocks.
Right. We synchronized the cooling of the primordial radiation, the nuclear decay of the oldest star clusters, and the relativistic rewinding of galactic expansion.
All pointing to one moment.
Then we established the absolute edge of causality at the 93 billion light-year cosmic horizon, accepting that our vision is literally walled in by the birth of time itself.
Because telescopes are time machines.
Exactly. Then we confronted the necessity of the inflaton field, which stretched reality by factors of 10 to the 26th power, making our vast observable universe a mere speck.
A rounding error.
Yeah. Then we looked at the smudges on the blueprint, the cold spots, the axis of evil, and we entertained the terrifying thought that our entire cosmological principle might just be an illusion of our local vantage point.
The CMB heresy.
Right. And finally, we found ourselves suspended as microbes in a single nucleated water droplet, adrift in an eternally inflating sea of inaccessible multiverses.
It's a humbling progression. Finding the edge of what can be known does not diminish the scientific endeavor, though.
You don't think it's depressing?
Not at all. Acknowledging these absolute physical barriers, the cosmic horizon, the opaque speed of light, the unreachable bubbles, is the maturity of cosmology.
Maturing how?
It is defining the exact horizon of science. It is the precise line where empirical measurement ends and profound mathematical wonder takes over.
The edge where measurement ends and wonder takes over. I love that.
It's a good place to be.
It is.
Yeah.
Now, I want to leave you with a final, slightly destabilizing thought to chew on as you go about your day.
Oh, boy.
We've spent this entire deep dive obsessing over time, right? Counting billions of years, tracing clocks, rewinding expansions.
Yes.
But if the eternal inflation model is right, if the overarching leaf of reality is constantly violently expanding, and our universe is just a localized droplet where that inflation happened to pause, then what does the concept of time even mean outside our bubble?
That is a deep question.
Think about it. Our thermodynamic clocks, our stellar decay rates, the geometry of our expanding galaxies, they all started ticking at the Big Bang.
Because that's when our physics crystallized.
But the Big Bang was just the end of inflation in our specific neighborhood.
Yeah.
If chronological time as we experience it is merely a byproduct of our local inflation stopping, then out there in the endlessly stretching void between the bubbles,
On the leaf.
yeah, out there on the leaf, linear time might not even exist. Asking what happened before the Big Bang or searching for an ultimate universal beginning might be the ultimate local prejudice.
We are imposing our local rules on the multiverse.
Exactly. We are imposing the rules of a single water droplet onto an ocean that plays by entirely different laws.